So, hello everybody. So now we will go to part 3 of chapter 2, which is modeling in the frequency domain. So we just need to continue the modeling part. So in this part, we need to talk about electrical network transfer functions. How can we find transfer function of electrical network? So we have this table in section 2.4 in the book. We have our LC circuit, and our LC circuit consists of inductance connected with resistance, and we have here a capacitor. So if you want, you have also this table, and this table, it represents the relationship between voltage, current, voltage, charge, and impedance relationships for capacitors, resistors, and inductors. And the capacitors, resistors, and inductors are the main component of our LC network. So in this example here, we have our LC network. If you want to find the transfer function of Vc of t divided by V of t, so we need to find the transfer function between the output to the input. The output here will be VCT, which is the voltage drop across the capacitor divided by the voltage drop of the input, which is a source. So one way for solving it, which is very quick, is to convert all those resistance, inductance, capacitance into impedance. So the impedance of L, it will be Ls. Impedance of R, it will be R. Impedance of C, it will be 1 divided by Cs. If you want to find this impedance, you can find it from this table. So the impedance of the capacitor, it will be 1 divided by Cs. Impedance of the resistor, it will be R. Impedance of the inductor, it will be Ls. So now we need to write the differential equation or the transfer function. So we just, we have our LC network, it consists of one loop. So we need to just label the current in it. So we can just draw a line from the source, going back again to the source, and we will call it I of t. And we will convert this one into Laplace transformed network. And in this case, we will replace inductance with Ls, which is the impedance of L. R, it will be R. C, it will be 1 divided by C of S. Vc of t, we will convert it into Vc of S, because this is in the S domain form of the time domain Vc of t. It is the same for the source also. The source will be capital of S. We will use Kirchhoff voltage law. So the summation of voltage of one side, it will equal to the summation of the voltage on the other side. Or you can say that with the source, the voltage drop across the source, V of S equal voltage drop across L plus voltage drop across R plus voltage drop across C. Voltage drop across L, it will be Ls multiplied by I of S. So if you want to see it here, it will be in the table. Voltage drop across L, it will be this one. Do you see this relationship? So in fact, this one means Ls I of S. This one means in S domain, it will be Ls, which is the impedance multiplied by the current, which is I of S. So it will be Ls I of S. As a voltage drop across resistance, it's R multiplied by I, and in S domain, it will be R multiplied by I of S. It is the same for the impedance of the capacitor. Voltage drop across the capacitor, it will be 1 divided by C multiplied by the integration of current. And when we differentiate, we multiply by S. When we differentiate, we will divide by S. So it is the opposite. So we can say that Vc of S, it will be 1 divided by Cs multiplied by I of S. So now we can take I of S as a common factor. So it will be Ls plus R plus 1 divided by C of S multiplied by I of S. But in fact, in our problem here, we need to find the transfer function between the voltage drop across the capacitor and the input. So we will substitute I of S by Cs Vc of S, because we need to find a relationship. We need to get Vc of S. So we can look into Vc of S. What is Vc of S? In fact, Vc of S, it's this one. We can say that Vc of S equal 1 divided by Cs multiplied by I of S. So just substitute the value of I of S, which is Cs multiplied by Vc of S. So do this substitution, multiply Vc inside. So this one will be Lc LCS square. This one would be it would be RCS. And this one, it would be 1 divided by C of S multiplied by C of S. So it will be 1. And there's a total multiplied by VC of S. We need to find the transfer function. So transfer function G of S, it would be VC of S, which is output divided by the input, which is V of S. So this one divided by this one, it will be the coefficient of this one, which is 1 divided by that part. So it will be 1 divided by LCS squared plus RCS plus 1. So try to make it beautiful, try to arrange. So divide by LC, so because we need to have here S squared, so it will be S squared plus RC divided by LC, it will be R divided by L multiplied by S, plus 1 divided by LC. Here also we need to divide by 1 divided by LC. If you want to convert this one into time domain, we need to see how much input, I mean V of S, it could be 5 volts, for example. So in this case, VC, it will be 5 divided by S. In this case, we can do cross multiply and get VC of S equal something, and we can use partial fraction expansion to find the inverse Laplace transform. We will go to a more complex example where we have 2 loops. So it's still RLC network, but it's more complex, as you can see here. So we have 2 loops. So the left-hand side, it's loop 1, which is closer to the source. You can say that, I mean, if we need to look into it, you can see that the current which is going out from the source, it will go into that direction. And we will reach this point here where we have a branch. So part of this current will go in that direction and the other part will go here. So we can say that one part, we will call it I1, and the other part will be I2. So just need to draw I1 and I2 and try to sum voltage around the 2 loops. But to make it easy for yourself, try to convert it from its form into impedance, into S domain. So we need to get the Laplace transform of this network. So in this case, we will change each element by its impedance. Impedance of R1, it will be R1. Impedance of R2, it will be R2 as it is because it's constant. Impedance of L, it will be LS. Impedance of C, it will be 1 divided by CS. That is it. And we will look into the first loop. This one, it's loop number 1 to the left. So this loop number 1, we will write the voltage across it. So it will be like this one. The source V of S equal R1 multiplied by I1, correct? I1 of S. So it will be R1 multiplied by I1 plus LS multiplied by I1 minus I2, because we have in this direction, we have I1, and in the opposite direction also we have I2. So the total current in LS, it will be a subtraction of I1 from I2. So it will be I1 minus I2. So just arrange it to get this equation. And for the second half, the second loop, it will be the same, but we don't have a source here, in fact, right? So in this case, we are starting maybe from R2. So it will be R2 multiplied by I2 plus 1 divided by CS multiplied by I2, which is a voltage drop across C, plus LS, right? Plus LS, this one, it's LS, in fact, multiplied by I2 minus I1. It will be I2 minus I1. And in fact, this summation equals 0 because in the second loop, we don't have any source. So in this case, we have 2 equations, equation number 1 and equation number 2. Try to simplify and solve for I2 of S, because we need to find the transfer function between I2 of S divided by V of S. So we have 2 equations here. We have 2 unknowns. Vs is known, in fact, because this is the input, but we don't know. We know R1, we know L, we know C, we know R2, but we don't know I1 and I2. So in fact, we have 2 equations and 2 unknowns. Those 2 unknowns is I1 of S and I2 of S. We need to solve it for I2 of S. So there is one nice approach for solving this. You can just arrange those 2 equations. This is again equation number 1 and equation number 2. Try to arrange it so we can have the coefficient of I1 of S in one side minus LS multiplied by I2 of S equal V of S. Also, we will arrange the second equation in the same way. So it will be minus LS multiplied by I1 of S plus this coefficient multiplied by I2 of S. If you want to solve it, in fact, you can just substitute, multiply by negative, subtract this one from that one until you find good expression for I2, which will take a long time. But one very efficient way for solving it using something called the Cramer's rule. And if you want to use this approach, you need to write those two equations in matrix form, matrix notation. So we can write those two equations as matrix multiplication, like A multiplied by X equal B, for example. It will be like this one, where X will be my states, my variables. It will be I1 and I2. So we will write it, we will use matrix notation. So first, in the first row, we will write the first equation. So in the first row here, in fact, we have equation number 1. And in the second row, we have equation number 2. In the first row, we will have R1 plus LS multiplied by I1. Do you know, in matrix multiplication, we multiply this row by this column, right? So R1 plus LS multiplied by I1 of S minus LS multiplied by I2 of S equal V of S. So this is equation number 1. We need to write equation number 2 in the same way. So we will start by writing the coefficient of I1 of S, which is minus LS. So we will have here minus LS multiplied by I1 of S plus that part. This is the coefficient of I2 multiplied by I2 equal 0. So now we have the two equations in matrix notation. We will use this Cramer's rule. And in this Cramer rules, if you want to solve for I2, we need to replace this column because this column is connected with I2. Those are the coefficient of I2. We will replace the second column with the output, V of S and 0. And we will take the determinant, right? So if you want to solve for I2, we need to replace the coefficient of I2 with the right-hand side, V of S and 0. If you want to solve it for I1, we will replace column number 1, which are the coefficients of I1 of S. So we need to get I2 of S, so it will equal determinant of this matrix. So we will keep the first column, and we will replace the second column with V of S and 0, and it will be divided by delta. Delta, it's the determinant of this equation. So let us find the determinant of this equation. So it will be that part multiplied by this one minus this one. So we can see it like this one. So it will be R1 plus LS multiplied by 0 minus V of S multiplied by minus LS. So it will be positive LS V of S. So determinant of this matrix, it will be LS multiplied by V of S divided by delta, which equal, in fact, LS divided by delta multiplied by V of S. We need to take V of S outside because we need to get the transfer function, which is I2 of S divided by V of S. So this transfer function will be LS. So in fact, this one should be LS divided by delta. So now we need to get delta. Delta will be determinant of this matrix. So it will be that part multiplied by this one. So this one, it's multiplication minus that part multiplied by that part. So it will be, I can write it in details here. So it will be R1 plus LS multiplied by R2 plus 1 divided by CS plus LS minus LS multiplied by LS again. So it will be minus. So this one, it will be minus L squared S squared. So it will be like this one. So do this multiplication and try to simplify it to get this equation. So just find the transfer function. So transfer function will be I2 of S divided by V of S. So it will be LS divided by delta. So it will be LS divided by that part. So just try to arrange it to make it looks beautiful. So this is the coefficient of S squared. This is the coefficient of S, and this is a real part here or scalar. So you can divide maybe by that part to make it looks more beautiful. So I can write it like this one. So it will be S squared plus R1 R2C plus L divided by R1 plus R2 multiplied by LC. This one S plus R1 divided by R1 plus R2 multiplied by LC. And here we will have LC squared. LC divided also by R1 plus R2. In fact, LC will cancel LC. So this one will be 1. S squared. So as you can see, it's second order system, right? So now we can get the transfer function of our system. So you can draw the block diagram. This one, we call it block diagram. So the block diagram now here, it will be like this one. When the input is V of S, the output is I2 of S, and this transfer function inside, it will map the relationship between V of S and I of S. So you can say that I2 of S equal G of S multiplied by V of S. So in fact, this G of S transfer function, it will transfer V of S into I2 of S, right? So this is a response. So if we need to plot this response in time domain, so we will have here time, we will have here the input, which is V of S, and after that we will plot the response, which is I2 of S. So it will be something like this one. So now we need to go for more complex example. And in this example, in fact, it's 3 loops. So we have here 3 loops. So if you need to solve it, you just draw. We need to start by drawing those currents and give it a label, just name it. So this one will be I1 of S. This one will be I3 of S or I2 of S. This one will be I2 of S. That is it. And after that, we will write the equation. We will look into the first loop. Maybe this is this one. It's loop number 1 where we have I1 of S. So if you want to write this equation, we will start from this resistance. I mean for I1 of S, we will have this one 1 plus 1 resistance plus 2 of S, because it's impedance. When it is impedance, in fact, you just add those impedances together. So we will have 1 plus 2 of S. So it will be 2 plus 2 of S multiplied by I1 of S. So this is a current in that direction. I2, it's working in the opposite direction, correct? So it will be negative 1 plus 2 of S multiplied by I2 of S. And also here, in fact, we will get part from I3 moving in this resistance, right? So it will be negative because it is moving. It moves in the opposite direction of I1. So it will be negative 1 multiplied by I3 of S equal the source, which is V of S. So this is equation number 1. If you want to get equation number 2, it will be the same, but in this case, the source equals 0. We will calculate the summation of voltage drop across the network. So it will be, we can start with I1 because we need to keep the order. So for I1, I1 is moving against I2, right? So it will be minus 1 plus 2 of S, minus 1 plus 2 of S multiplied by I1 of S. We will go to I2. For I2, it will be positive. So it will be 1 plus 4 of S plus 3 of S plus 2 of S. 4 of S plus 3 of S, it's 7S plus 2 of S, it will be 9S. So it will be 1 plus 9S multiplied by I2 of S. We will look into I3 because part of I3 will go through this R of S. So it will be minus 4S multiplied by I3 of S equal 0. So this is equation number 2. We will go to loop number 3. We will start also with I1 because we need to keep this order. If we will use Cramer rule, so it will be I3 is moving, I1 is moving against, in fact, I3. So it will be 1 minus 1 multiplied by I1 of S. We will go to I2. So I2 also, it's moving against, you see, this is I3 moving in that direction, and the I2 is moving in that direction. So it's moving in the negative direction. So the contribution of the voltage across 4S, because of I2, it will be negative 4S. It will be negative 4S multiplied by I2 of S, plus the rest multiplied by I3, which is 1 plus 4 of S, right? It will be 1 plus 4 of S plus 1 divided by S. So it will be like this one, multiplied by I3 of S, and this one will be equation number 3. As you can see here, we have 3 equations. We have 3 unknowns. Those unknowns are I1 and I2 and I3. Solve it in any way, right? So, and after that, you can, if you want to solve it for I3, for example, you will get I3, and after that, you can write the transfer function, which G of S equal, for example, it would be I3 of S divided by the input, which is V of S. So you can write this transfer function in this way. So this matrix will be 3 times 3. Yes. So, so just if we want to write the equations one more time, as I told you, so we have loop number 1, loop number 2, loop number 3, right? So we will look into loop number 1. So the input here is V of S. We have I1 of S. Try to write it in order. So it will be 1 plus 1 plus 2 of S. So it will be 2 plus 2 of S multiplied by I1, right? We look into I2. I2, it will be negative 1 plus 2S multiplied by I2. I3, it will be negative. It will be negative I3 because this is the voltage drop which will generate it across this resistance as a result of I3. So it will be like minus I3 equal V of S. This is equation number 1. Equation number 2, one more time. We will start with I1 to keep this order. So it will be I1 is moving against I2. So it will be negative 1 plus 2S multiplied by I1 plus, what about I2? Or it will be positive. It will be 1 plus 4S, 3S, 2S. So it will be 1 plus 9S multiplied by I2, negative I3 multiplied by 4S. So it will be 4S I3 equals 0. So this is equation number 2. Equation number 3 for loop number 3. It will be also, we will start with I1 to keep the order. So it will be negative I1 because I1, it will generate voltage drop across this resistance against in the opposite direction. Negative I2, it will be RS, it will be negative 4S multiplied by I2 plus maybe 1, plus 1 divided by S plus 4S multiplied by I3 equals 0. This is equation number 3. And after that, you will use matrix notation and you will write it in matrix form. In matrix notation, it will be like this one. It will be large matrix multiplied by coefficient, which is I1, I2, I3 equal the output, which is V of S 0, 0. And we will write here the coefficient. So the line number 1, it will be, here we will get here 2 plus 2S. Here we will be negative 1 plus 2S. Here it will be minus 1. So this is the coefficient of I1. We will go to the coefficient of I2. It will be negative 1 plus 2S and so on. So we will write all those coefficients. And now we have our system in matrix notation where we can use Cramer approach or rule for solving it. So in section 0.25, we will go to translational mechanical system transfer function. So it's a mechanical system. And we have this, it's called force velocity, force displacement, and displacement translational relationship for spring. And we will focus on spring, damper, viscous damper, and the mass. And the spring, it will generate a force. In fact, this force is proportional to, do you see here? It's proportional to the integration of the speed, and the integration of the speed is the distance, correct? In fact, or differentiation of speed equal distance. So anyway, if you have a spring, when you pull it in one direction, it will generate a force to resist you. This force will be equal to K multiplied by displacement, X. So as you can see here in this figure, we have this spring. It has a coefficient, K, because not all springs are the same, are similar. So some of these are very strong, some of these are less stronger. For example, so it has a coefficient called K. So if you try to drag this one, if you try to drag the spring into the right direction, in fact, it will generate a force against you to resist this. This force will be proportional to the displacement. So this force will be K multiplied by X. If you want to put it in S domain, so it will be, the impedance will be K, of course, but the impedance, it will be K, or resistance, it will be K. And if you want to put this one in S domain, so it will be like F of S equal K multiplied by X of S. So that is it. For the damper, it's the same. If you try to drag this the damper into the right direction, it will generate a force to resist you. This force will proportional to the speed, right? So this force will be proportional to the speed. So it equal FV multiplied by the speed. And the speed, in fact, it's dx by dt. The speed, it's the rate of change of distance. It's dx by dt. So if you want to write it in S domain, so it will be F of S equal FV multiplied by Sx of S. So in this case, we can say that the impedance of that part is FV multiplied by S. For the mass, it's the same. If you try to drag something heavy, in fact, its weight, it makes friction. And this, it will generate force, and this force will be proportional to the acceleration. So it will generate a force called F of t, and this force will be proportional to the acceleration, and the acceleration, it's the rate of a change of speed. So it will be a force proportional to dv by dt. So this force will be m multiplied by dv by dt. We can say that it's m multiplied by a, which is the acceleration, or you can just say that it's m multiplied by d squared x by dt squared. If you want to put it in S domain, so it will be f of s, it will be m s squared x of s. So that part will be the impedance. So the impedance in this case, it will be m squared. So this is the table for translational mechanical systems. So now we need to use an example. And in this example, it's one equation of motion. And in this example, we need to find the transfer function x of s divided by f of s. So the output here, in fact, it will be x of t, which is a displacement. You have a system, and the system is connected to the wall. And you try to apply force on that system and try to drag it into the right-hand side. So, of course, when you do this, it will generate forces which will resist you. Those forces will be force from the spring. It will be K. The impedance, it will be K. Or it will be K multiplied by distance. And the number, it will generate a force. It will be FV multiplied by speed. Or you can say that it's FVS x of s. M, it will generate also a force. So this force will be proportional to acceleration. So if you want to put it in S domain, so it will be M multiplied by S squared x of s. So if you want to solve this equation, if you want to find the transfer function, we need to start by drawing the free body diagram, where you place on the mass all forces felt by the mass. We assume that the mass is traveling to the right side. So we only the only applied force points to the right. All other forces which impede the motion and act to oppose it, it will be to the other. So it will point to the other side, which is the left side. Write the differential equation of motion using Newton's law to sum to zero all forces. So now we need to solve this equation. First, this is a free body diagram. So we will draw the free body diagram, and then we will put all forces and inputs. So you have f of t, which is the input. In fact, if you go to the gym, you try to apply force on a body, and this try to drag it to the right-hand side. So you apply force. So this is your force, in fact. And you need to, it is stand still at some location at x equals 0, in fact. So at some point, it's just stand still here. It's not moving. And then when you apply force and try to drag it to the right-hand side, what will happen? This one will move, in fact. So you can just drag it a little bit. So it will move to that place. So what will happen here when we move it to that direction? I mean, x was 0, now x has a value, correct? A displacement, there is a displacement. Maybe you moved it by 1 meter, for example, correct? So you are moving it into the right direction. You try to drag it to change the displacement from 0 to 1 meter or 2 meters. So in this case, when you try to do this, there will be forces which will be generated on the opposite direction because it try to oppose you. The first one, which is a force which is generated by the spring, and it's K multiplied by x of t. It's proportional to the displacement, so it will be K multiplied by x of t. Also, the number, it will generate a force which will be proportional to the speed. So it will be Fv multiplied by dx by dt. Remember, dx by dt, it's the speed. This one is speed. But x of t here, it's displacement or distance, displacement. The same way also this mass itself, it will generate a force, or it will maybe generate force, and this force will be proportional to the acceleration, right? So it will generate a force which is m multiplied by d squared x by dt squared. D squared x by dt squared, this one is acceleration, right? So in this case, we will write it in Laplace transform. So those are the forces which are acting in you. F of s, f of t, it will be converted into f of s. X of t, it will be converted into x of s. The Springer, it will generate force equal kx of s. The number, it will generate a force equal to Fv multiplied by Sx of s, correct? Because dx by dt, it will be Sx of s. And the mass, it will generate a force equal ms squared x of s. Because d squared x by dt squared, this one is transformed, it will be s squared x of s. So now we will use Newton's law to write the sum of equations, the sum of forces. Forces acting on this side will equal to the forces acting on the other side, correct? So the summation of forces in this right-hand side, left-hand side, it will equal to the forces acting on the right-hand side. So the summation of forces here, it will be, we can start with the higher power. So it will be ms square x of s plus, if we go from down to top, from bottom to top. So it will be ms square x of s plus fvs multiplied by x of s plus kx of s equal f of s. Take x of s because x of s is a common factor here. Just take it as a common factor. So what will remain will be ms squared plus fvs plus k all multiplied by x of s equal f of s. We need to get the transfer function, which is x of s divided by f of s. So we need to divide both sides by this coefficient, right? We need to divide first by that part, and after that divide by that part, so we can get x of s divided by f of s in one side. So what will remain here, it will be 1 divided by ms squared plus fvs plus k. So just to do this division step by step, this equation divide both sides by ms squared plus fvs plus k. So it will be like x of s equal f of s multiplied by divide by 1. So it will be ms squared plus fvs plus k. And again, divide both sides by f of s. So it will be x of s divided by f of s equal that part, which is ms squared plus fvs plus k. So now we have this is my transfer function. We'll call it g of s, which is the output divided by the input at zero conditions. So draw block diagram. You just put this transfer function in the block, and then when the input is f of s, the output should be x of s. So the idea here, if we apply 0 power, this one will be 0. It will not move because it's a standstill. And if you applied some power here, some newtons, for example, how much power you would apply here, x of s will increase from 0 to some this, because you try to push, you try to drag this object to the right-hand side. So this is a nice example because it's only one block, one equation. We can take more complex example. So one more time here, if you want to solve it one more time, sum of forces here will equal to the summation of forces acting on that side. This one should be equal to this one. So it will be like this one. It will be m s square x of s plus fv s x of s. You just put it in s domain directly, plus kx of s equal f of s. Take x of s as a common factor. So it will be ms squared plus fv s plus k all multiplied by x of s equal f of s. We need to get the transfer function. So transfer function called equal x of s output divided by input, which is, if this one is the input, of course, because if you are in the gym and playing something, you are providing input to the system, and the system will move. So the input is force and the output will be displacement. So this one will be 1 divided by ms squared plus fvs plus k. So it will be like this one. Draw block diagram, write your transfer function here. The input will be f of s and the output will be x of s. Now you have your system ready for modeled. The system is modeled. Okay, so we will go to the second example. And the 2 degrees, we have assessed a more complex translational system, but we have 2 degrees of freedom. 2 degrees of freedom means I can move M1 and keep M2 standstill, or I can move 2 and keep M1 standstill. So it means you have 2 degrees of freedom. But in the previous system, it has only 1 degree of freedom because we have only one object. We can just move it or leave it, right? But in our system here, what happened? In fact, I can move M1 alone, I can move M2 alone, or I can move both M1 and M2 at the same time. So now we need to find a differential equation which describes this system. So he asked us to find the transfer function, which is x2 divided by f of s. We need to see where is f of s. Now we have, this is the input to your system, right? This is f of t. And we have 2 displacements. M1 will move by x1, and also M2 will move by x2. So we need to find relationship between x2 of s and f of s, x2 of t and f of t. If we will push M1, do you think that M2, x2 will change? Yes, I mean, if you will push it to the right-hand side, if we will push M1 into that direction, in fact, it will K2 and the number here, it will generate a force which will try to push M2 to the right as well, right? So of course we can have this. So to solve this problem, we need to use something called the superposition theory. And it's something where we try to divide the problem and simplify the problem, and after that combine the equations of motions. We use the superposition to do the free body diagram. First, we need to hold M2 stand still. We need to keep M2 stable, and we will move M1 to the right and define. So we will keep M2 stand still, and we will move M1 to the right, and we will find the forces which are acting on M1. And after that, we will hold M1, and we will move M2 to the right, and we will find the forces acting on M1 again. And at the end, we will sum the forces acting on M1 using the superposition. And at the end, we will write an equation describing motion of M1. And we will do the same for M2. So let us start with this step number 1. So here what will happen? We will keep M2 stand still. First, of course, it will be nice if we can just use impedance instead of, but anyway, we will try to keep M2, hold M2. So hold M2, M2 will stand still, right? And we will move only M1 to the right. We will move M1 to the right. And we will see the forces which are acting on M1. What will happen here if we will move M1 to the right? What will happen? Yes, there will be some forces which will try to resist this movement. So we have only f of t, which is acting on the right-hand side. So we have f of s. We will write it f of s here on that side, that it's acting on that direction. And we will see the other forces. So the other forces first, we will have K1. This K1, it will resist you, in fact, right? It will resist you. It will generate a force in the opposite direction because it doesn't like to move, in fact, because it is connected to the wall, and it will try to reject or to resist this movement to the right side. So it will generate a force in the opposite direction. K1 will generate a force, and this force will be proportional to the distance, which is x1 of s. So it will generate a force called the K1 multiplied by x1 of s. What else will happen? Yes, we have also M1 itself. It has a weight, and it will generate a force which will try to resist this movement. This force, it will be M1 s squared x1 of s, because this force is proportional to the acceleration. So this is also one force. At the same time, also we have this damper. It also will generate a force which will reject this movement. So it will generate a force which is proportional to the speed. So it will generate a force in the opposite direction called FV1 multiplied by Sx1 of s. So this is very good. What else will happen? Yes, we have also here damper FV3 and a spring called the K2. If you try to move M1 to the right-hand side, also this damper, it will generate a force which will resist you. So it will generate a force in the opposite direction, and this force will be proportional to the speed. So it will generate a force called FV3 multiplied by Sx1 of s, because it's proportional to the speed. At the same time, K2, it will generate a force also, which will resist the movement to the right-hand side, and this force is proportional to the distance. So it will be K2 multiplied by x1 of s. So now we have all forces acting on our body, M1, when we try to move M1 to the right-hand side. So now we will go to the second step, and in the second step, we will hold M1 stand still. So I will keep M1 as it is, and we will move only M2 to the right side. So I will try to move M2 to the right-hand side, as you can see here in figure A. So what will happen? So in this case, in fact, when you try to move this one to the right-hand side, we need to find the forces which will act on M1. If you will try to drag M2 to the right-hand side, in fact, FV3, it will generate FV3, it will generate a force. In fact, when you try to drag this one to the right, this one also will be dragged into the right. It will generate a force to act on M2, but this is not our problem now. We try to find forces which will act on M1. It will generate a force acting in that direction, because if it is connected to the wall, it's okay, but it's connected to M1. So it will try to drag M1 to the right. So it will generate a force to the right, and this force will equal FV3 multiplied by Sx2 of s, right? Because x2 of s is a changed, but x1 of s is still 0, right? So it will generate, which will proportional to the speed of M2. This force will be FV3 multiplied by Sx2 of s. In the same way, we have K2. K2 also, it will try to drag M1 to the right-hand side. So it will generate a force which is proportional to X2. So it will be K2 multiplied by X2 of S. So now we have all forces which are acting on M1 and M2. According to the superposition, we will just do summation, just sum all those forces. So try to find the forces which are acting to the right-hand side and forces which are acting to the left-hand side, and try to sum it together. So when we do the summation, we can start with K1, for example, right? K1 X1 of S, it's acting on the left side, and we have here K2 multiplied by X1 of S. So just take X1 of S as a common factor. So we will have K1 plus K2 multiplied by X1 of S. So this is the first power force. As a second force, for example, due to the number, so it will be FV S X1 of S. It will act to the left-hand side. What else also? What else? We have this one also, FV3, correct? So we will take X1 of S as a common factor, X1 of S as a common factor. So what will remain will be FV1 plus FV3. And of course, F of S is acting to the right. So this one will be to the right direction. This one will be acting also in the right direction. This one will be acting on the right direction, and also this one will be acting on the right direction. What will remain here, it will be M1 S squared X1 of S. So now we have all forces. We just need to write the equation. So from this total forces acting on M1, we will try to write equation of forces in this one. So just write it. So the summation of forces acting on the left-hand side, the sum here equals the sum here, right? Correct? Or just subtract. So it will be we will start with S squared. So it will be M1 S squared, correct? M1 S squared plus FV1 plus FV3 multiplied by S. We will take X1 of S as a common factor, plus K1 plus K2 multiplied by X1 of S. This is coefficient of X1 of S. What about X2? So X2, it will be negative. We will have here negative because it's acting on the right, but we will move it to the other side, so it will be negative FV3S plus K2 multiplied by X2 of S equal F of S. F of S is the input. So in fact, so the input here will be in one side and other forces will be on the other side. So now we have this equation. We have this equation. We will do also for we will do the same for M2, right? We will do the same for M2. So for M2, it's the same. We will use the superposition theory. So we will start with the figure with the first figure. So hold M1. We will start by try to find the forces which are acting on M2 due to the motion of M2. So we will hold M1, stand still, and we will move M2 to the right-hand side, and we will find the forces acting on it. So hold M1 and move M2 to the right-hand side, as you can see here, and we will find the forces acting on it. When we drag M2 to the right-hand side, what will happen? We can see that this spring K2, it will resist this movement. It will generate a force proportional to displacement X2, so it will be K2 X2. And the number here, it will generate a force. We have FV2, it will generate a force proportional to the speed of M2. So it will be FV2 multiplied by X2 of S, right? So it will be that part. And also we have FV3, it will generate a force proportional to the speed of M2. So it will be FV3 multiplied by X2 of S. M itself, it will generate a force proportional to the acceleration of M2. So it will be M2 multiplied by S squared X2 of S. All those forces will act on the opposite direction. In fact, also case 3 here, it will try to resist this movement to the right direction. So it will generate a force which is acting to the opposite direction, to the right-hand side. So to the left-hand side. So this force will be K3 proportional to the displacement. It will be K3 multiplied by X2 of S. So those are all forces acting on M2 when we are holding M1 stand still. We will do the opposite now. We will keep M2 stand still, And we will try to move M1 to the right side. So just move M1 to the right-hand side, as you can see here, and we will see what forces will act on M2. So in this case, when you try to push this one to the right-hand side, what will happen? In fact, FV3 and the K2 try to resist this movement. So it will generate forces in M2 to the right side. So it will generate a force acting in M2, which will try to push it to the right-hand side. So K2, it will generate a force proportional to X1. So it will be K2 multiplied by X1 of S. And also FV3, it will generate a force proportional to the speed of M1. So it will be FV3 multiplied by Sx1 of S. So now we have the forces. Using superposition, we will just add those forces together, but just consider the direction. So as you can see here, all forces in figure A are acting to the left-hand side. Forces in figure B are acting to the right-hand side. So just take the summation, as you can see here. Just draw those one here to the right-hand side, and those ones take summations and put them in this left-hand side. So we will have here a K2 plus K3. So it will be K2 plus K3 multiplied by X2 of S. We will have FV2 plus FV3 multiplied by Sx2 of S. We will have M2 S squared multiplied by X2 of S. And on the other side, we will have K2 multiplied by X1 of S and FV3 S X1 of S. So we will write this equation, just write it. So it will be summation on forces to the left minus the other to the right equals 0, correct? Because we don't have any external forces. We will write it as you can see here. We will take Xt of S as a common factor because this is common factor. So it will be M2 S squared plus FV2 plus FV3 multiplied by S plus K2 multiplied by K3, all multiplied by X2 of S minus the other side, which is FV3S plus K2 multiplied by X1 of S equals 0. So now this is equation number 2. Once you have equation number 2, now we have two equations. This is equation 1. This is equation number 2. Try to arrange it. So we're starting with X1 of S. And try to put it in matrix notation because we need to use Cramer's rule. So just take the coefficient. It will be like A multiplied by X equal B, for example. It will be like this one. So this first matrix, it will be the coefficient. The second matrix will be the distances or the states equal forces, which is this one. If you want to solve for K2, for X2, what will happen? Just replace this column with the coefficient of X2 with the output F of SV, and it takes the determinant. So it will be that part multiplied by 0, negative this one. So it will be that part divided by delta multiplied by F of S. And the delta, it will be determinant of this matrix. So now we can find the differential equation of our model. So quickly, we need to finalize this unit by section 2.10, where we try to talk about non-linearities. We just quickly, it's a linear system has two advantages. It's superposition, which means the output response of a system to the sum of inputs is the sum of the responses to each individual input. So something called the superposition. So if you have a system and if you act on this system with an input equal R1 of t, you will get C1 of t. If you are acting with R2 of t, you will get output equal CT of t. If you are acting with R1 plus R2, your response will be C1 plus C2. Homogeneity also, multiplication of an input by a scalar will yield a response which is multiplied by the same scalar. So if you are applying R1 of t, getting C1 of t. If you are applying a scalar constant multiplied by R1 of t, the output response should be C of t multiplied by that scalar. So those are, so in fact, you are using those points to check if your system is linear or not, non-linear. Examples of physical non-linearities, we have some amplifier saturation. And if you have an amplifier and you try to use a knob to increase the power, output power, you will be able to increase it in a linear way for a period of time. And after that, it will be non-linear, correct? So when you're pushing the knob more, you will not be able to get the accuracy, the power which you are expecting. And at some point, it will be saturated. You see this one? So this is a kind of saturation or a kind of non-linearity. We call it amplifier saturation. We have also a dead zone in motors. if you have an electric motor, for example, and you try to apply power on it, when you start by applying a power going from 0, for example, it will not move, maybe 10 volt, 20, 30, and at some point it will start moving. It will not move immediately when you apply volt, but it will take time to start moving. We call it dead zone, for example. We have also something called backlash in gears, for example, and this backlash, it's due to wear and tear in gears, for example. So you apply power, and those gears will start to move, but it will not start to move your vehicle because there is some gap between the tiers of the gears. So saturation nonlinearity, it's an electronic amplifier is linear over specific range of input, but shows nonlinearity called saturation at high input voltage. At high input voltage, you will not be able to get the same output. Saturation point is a point where an increase in input power does not produce the desired increase in output power. You try to increase the input power, but when you increase it, you will not be able to get what you are expecting because there is limitations or saturation. So even if you increase the input power too much, you will not exceed this limit or output power because you are in saturation. Dead zone also, when a motor does not respond at very low input voltage due to frictional forces. When you apply small voltage, you will not be able to get output, which is rotation. So you apply a voltage here starting from 0, maybe 20 volts, for example. During this period, the motor is not moving. So RPM equals 0, but at some point it will start to move. So we call it dead zone, and it's a kind of non-linearity. Backlash in gears, mechanical gears also are essential component used to transmit motion and power between shafts. So gears also that don't fit tightly shows this kind of non-linearity when the input moves over a small range without the output responding. It could be due to teeth wear and the center distance between gears. So this is a kind of non-linearity. And if you need to linearize, I mean, we are working in this course with linear system, but if it happens that you have a nonlinear system, you need to linearize the system around an operating point. So we need to decide that, okay, we need to assume that our system will be working around this operating point, and we need to linearize my system at around this point. So we assume that around this point, my system will be a linear system. So I will not talk about this example. We will just I will not explain this. Maybe how can we linearize the system? Maybe we can do it later on after moving in the course. So it will be much easier for you to understand. So now we finished chapter 2. Please, you have some review questions in page 87 in the book. Try to answer those questions and also try to study, solve, and simulate example 2.7 in page 81. So thank you very much for attention. And please, if you have any questions, just contact me. Thank you very much.